Good morning. We'll get started here in just a minute. Oh, shit. Hold on, there's something on my finger that hurt. Okay, I sent out an email a little while ago with the exam for review. So check your Canvas email. That should have gone out to you. And what I'd like to do today is finish up what we were talking about last time. All right, which is this whole idea of our exponential growth decay model. So I'm going to do another example like this. And then once we finish this, we'll be done in terms of the material on the test. So I'm going to bring up the review and we're actually going to work through the review. All right, so that's the plan for today. And then Tuesday, of course, is going to be the test. So just make sure you're here for the test. Same thing as normal. Make sure your computer's set up and all that, and we'll get it all going. So without any further ado, let's go ahead and get started here. So I'm just going to copy this over, and that way I have it and I don't have to redo this. It's the 19th. Is that right? Yeah, okay. Okay, so this is our exponential growth and decay model that we can use for anything that either grows or decays exponentially. And so the example I gave you last class was how we use this model to determine how old something is using what's called carbon-14 dating. But I'd like to do a different example, an example that's going to be more like the one that is on your review. So I think something that's easy to kind of understand is, you know, people take medication, right, for certain things. Maybe you have a headache, you take some Advil or something like that. And that drug is then in your system, and then it slowly kind of goes away over time. So different drugs have different half-lives. It's the amount of time it takes for half of the drug to go away. So the example that I gave on the review is specifically for Advil or ibuprofen. So the example I'm going to do right now, I'm going to do something different. So I'm going to let you all choose. Is there a particular medication you want me to look up the half-life of? Something that you might take, or not you take, but you know, that people take. I don't know. Any recommendations?
Zoloft.
Zoloft? Okay, let's look it up. Zoloft half-life. I'll show it to you in a second once I bring it up here. Okay, here we go. So we're just going to go off of this. I guess that's the generic name for it?
Yeah.
Okay. So it has a half-life of about 26 hours. All right. So I'm not sure what Zoloft's for. Is that important or no?
No, it's just for like anxiety. A lot of people take it just to help with it.
Okay, yeah, Zoloft, anxiety. All right. So we've got this drug Zoloft. It has a half-life 26 hours. Now, what I also need to look up to be able to do this problem is what like a normal dosage is. So let me just put here normal dose. Ooh, I'm not going to find anything. 50 milligrams. Okay, I'm just going to go with the first number I see there. I'm just going to put this on the side so I have it. 50 milligrams is a dosage. Okay, so we're being told that Zoloft has a half-life of 26 hours. I want you to really understand what that means. So I'm not actually getting to the problem yet. I just want us to all be clear on how half-lives work. So if someone were to take 50 milligrams of this Zoloft, let's just imagine, you take it, and let's just use a bar to represent the 50 milligrams. So that's how much is in your body at the time you take it, right? Well, in 26 hours later, half of it will be there still. So you'll have 25 milligrams still in your body. And then 26 hours after that, half of that will be there. So now you'll have 12.5 milligrams still in your body. So now what? That's 40, that's 52 hours later, you still have 12.5 milligrams of the original 50 you took. Does that make sense? And then this keeps on going, another 26 hours. And now you've got half of that. So that's what, 6.25 milligrams. And then another 26 hours, it's going to be half of that. So that would be 3.125 milligrams. Now, I'm sure that with Zoloft, once you get down to a certain amount, like once you get down to, I don't know, I'm not sure, I'm just guessing. And once you get down to something like this, it really is not having an impact on you. Like you're not, it's not effective. You probably have to have a significantly higher dosage in your body for it to actually work for you. So, but the thing that you need to understand is that it takes quite a while, doesn't it? For it to like get down to almost a negligible amount. I mean, we keep on having to do this. You go again, you're going to be about 1.5-ish, go again, 0.75, go again, I don't know, I'm just making this up, 3.75, something like that. So, how many, each one of these is like a day. So 1, 2, 3, 4, 5, 6, 7, a week later, you still have some traceable amount in your body. And that's assuming you just took it and you didn't take any more. I mean, your doctor might be saying you have to take 50 milligrams every day. So this is just what would happen if you just took one dose, what would happen over time. But do you understand the half-life idea? It just keeps getting half and half and half and half. And the amount of time it takes for that to happen depends on the medication. I mean, Zoloft, it's 26 hours. The review I made for you, the last problem on this one is I give you that the half-life of ibuprofen is 3.5 hours. So for Advil, painkiller, that's a painkiller. 3.5 hours after you take it, half of it has already been absorbed and it's no longer having an impact on you. And that's why they say you should only take Advil like every 6 hours or so, is because you need it to like, half-life down a little bit before you put that dosage back into your body. Anyway, this all clear? I want to be able to move on to the actual work. I just want to make sure everyone understands the half-life concept. Any questions? No? Okay. So here we are. We've got Zoloft. Half-life we know is 26 hours. And by the way, they figure out the half-life by doing experiments. They measure it. Okay, they give it to someone, then they measure how much is in their blood and stuff like that. So this is known. All right, so first question here, the first thing that we're going to do is we're going to use the formula P equals P sub 0 E to the KT to find what we'll call the model for Zoloft's decay. In other words, what's happening is over time, the Zoloft in the person's bloodstream is dying down, right? So it's a decay. It's not a growth, it's a decay. The model we're looking at here can be used for both growth and decay. For us in this problem, it's a decay model. So we want to use this model to find, or use this equation to find the actual model for Zoloft specifically. Now, What that means is, at the end of the day, what this really means is that we need to go find what K is in this model. So K is this number right here. And once we know K, then we can answer any questions that anyone ever asks us about Zoloft. But we have to find the K first. So here's how I do it. Remember, P on this side, on the left side, is the amount that should be in the, the amount, let's say in terms of the Zoloft, the P should be, the left side should be the amount of Zoloft that's in the person's body at some specific point in time. P0 is the initial amount, okay? And then K is what we call the growth or decay constant, and then T is the time. So using the fact that it takes 26 hours for half of it to go away, watch what I'm going to do with this equation. And you would do this on every single problem that gives you a half-life. What you do is you say, okay, let me write the equation down here. You say, all right, well, if I take some Zoloft, and forget the 50 milligrams right now, okay? Let's say you just take some Zoloft, then in the beginning, you're going to have 100% of the Zoloft in your body. Whatever it is you take, it's all there, right? So we're going to replace that initial amount, okay, with 1. And the 1 is representing 100%. So if I were to ask you to convert 100% to a decimal, you would move the decimal 2 places to the left, and you would get the number 1. So this 1 right here represents the amount, the fact that we took something, right? Who cares how much it was? We took some. We have 100% of it now in our body. Now, the rest of this is e to the k. Now, what we know, we don't know k, but we know that the time that it would take for half of it to be left in our body would be 26 hours. So I'm going to put 26 here. And that should be equal to, well, you tell me, how much, if we started with 100% and we're looking at what happens 26 hours later, how much should be left after 26 hours?
25?
Okay, so you're still thinking of the 50 milligrams. Forget the 50 milligrams for now. Look at it as a percentage. We started with 100%, right?
Mm-hmm. So it would just be 50?
50%, right? 50% is what should be left, half of it. So I'm just going to put here 0.5. That 0.5 comes from the idea that we should now have 50% left after 26 hours. So what I'm telling you is this: no matter what the problem is, okay, if it was Zoloft, if it was Xanax, if it was, no matter what the drug is, no matter what it is you're ingesting, once you have the half-life will always go here. Okay, that number will always go there. And you will always use the number 1 and the number 0.5. You'll always do that when you're trying to solve for K, every single time. All right, because that's what half-life is all about. You start with 100%, you end with half of it. And this is the amount of time it takes for it to happen. Do you all see that this equation that we have here is an exponential equation? In other words, we only need to solve for K. K is the only variable here, and that's up in a power, so we need to get it out of there. Now, there's some good news that this 1 in front of the E, we can ignore it because 1 times that is just itself. So I can do this. And does someone want to tell me how I could get this K out of here? If I have E raised to the 26K, how can I somehow do something to get that K to actually come down? How do you kill E?
Is this where we bring the natural log in?
That's right. This is where we bring in the natural log. Good, Carolyn. So here what we're going to do is on the left side, we're going to take natural log of 0.5. And on the right side, we're going to do natural log of E to the 26K. The whole reason we do it is on the right side, the natural log and the E will kill each other off, which just leaves you with the 26K. And on the left side, well, you got to get your calculator out. And you got to take the natural log of 0.5. So who wants to give me that? I feel like I need to call on some people today or something, because there's always the same people answering. Not that I don't want to hear the same people, but natural log 0.5,
Negative 0.693.
negative 0.693. Okay. And I would say that on the test, you know, just go as many decimal places as you feel. You don't have to put 10 decimals out. I'll just say that the more decimals you go, the more accurate your answer is going to be. Let's just go with that. Okay.
Wait, so I have a question.
Yes.
How did you get rid of the 1, or did you just like pretend it's not there because it's 1?
Yeah, I just pretend it's not there because it's 1.
Okay.
1 times anything is itself. So we have one more step before we can find K, right? We got to get this 26 out of here. So how do we get rid of that 26?
Divide both sides.
Yeah, just divide, right? We're just going to divide both sides by 26. So we're going to need our calculators again. We're going to divide by 26 here, divide by 26 here. That'll leave us with K equals negative 0.693 divided by 26. So I'm getting negative 0.02. I'm going to go 6654. That's how far I'm going. Okay. This is our answer, but it's not the final answer for part A. This right here is what we call the decay constant. That's the decay constant. Every single substance out there that decays, okay, that has some sort of half-life to it, will have some decay constant that corresponds to that substance. So this is Zoloft's decay constant. If you look back at last class when we were doing the carbon dating, carbon 14, we went through this same exact sort of process, and we found the decay constant to be this. All right, that's what we did last class. So this time we have something different decay constant. Here it is. So now to answer part A, okay, here's the answer to part A. What I'm going to do is I'm going to take this model that we have and I'm going to rewrite it. But now I will replace K with what I just found, negative 0.026654 T. Okay, this right here is the decay model for Zoloft. So that means we have found like the master formula that we can now use to answer any question. All right, so if anyone asks us anything about, hey, you know, if you take some Zoloft, how long is it going to take for it to go away? You know, we can answer anything just based off of this equation. Any questions on this? This is just the setup. Okay, let's do part B. So part B, what I'm going to ask you is this. If you take, let's go with the 50 milligrams of Zoloft, how long will it take to have 2 milligrams remaining in your system? And by system, I mean like your bloodstream, whatever in your body, right? That's the question. All right. So this is our master formula that we get to use now. Remember, what was P sub 0? This right here, that P sub 0 represents the initial amount. So that's the amount that we're going to take in the beginning, right? So the initial amount, do we know what that would be? How much are we going to take? 50?
50.
Right, 50. How much do we want at the end? We want to know how long it's going to take, right? How long means that we want to find T, right? We want to know what T is. And let me label this. The 50 milligrams is how much we're going to start with. And we want to know how long, so we want to know T in order to end up, right? And ending up is the left side of the equation. We want to know when that's going to be 2. So if we start with 50, we want to know how long it's going to take to get to 2. So all I'm going to do is rewrite that equation. I'm going to replace the P with 2. I'm going to replace the P sub 0 with 50. And then e to the negative 0.026654 times t. There we go. And now our goal is to solve for t. Let's go ahead and do that. So what should we do first? Let me call on somebody. Go. Let's see who's around today. Who have I not called on in a while? Let's see. How about Leah? Is Leah around today?
Yes.
How's it going, Leah?
No.
Any ideas on how we would go about solving for T here?
I know it has something to do with logarithm or logarithm.
Yeah, the logarithm is going to come in. We're definitely going to need the log to kill the e, right? But you have to be real careful because when you do the logarithm, you have to have this by itself first, Leah, before you can do log on both sides. So if you were trying to get this by itself, how could you get rid of this 50?
Divide.
Yeah, so let's just do that. We're just going to divide both sides by 50 first. Okay. And we'll need our calculator for that. Okay, so we'll just do 2 divided by 50, right? That's going to give us a decimal. And Leah, do you have a calculator?
Yeah, it's
Okay.
0.04.
0.04, good. And then now at this point, Leah, you can do the natural log on both sides of the equation. So we're going to do the natural log of the left side.
Yeah.
And then we're going to do the natural log of the right side. On the left, what'd you get, Leah?
The left, I got negative 3.21.
Yep, negative 3.21. And I'm just gonna go one more decimal. I'll put 8. I'm not gonna be real big on this, you know. Once you go a few decimal places, but and then on the right side, the whole idea was the right side, the natural log and e go away, right? So all we're left with is the negative 0.02665 t. Okay, good, Leah, you're off the hook. How about, where was I? How about, is Victoria around? Victoria?
Yes.
Okay, are you following along, Victoria?
Yes.
Okay, so what would be next?
You would divide the
Mhm.
negative 0.026654.
Yeah, we're going to divide this on both sides.
Yes.
There we go. That's it. And that should give us our t. I'll go ahead and let you do that. On the right side, we get t because they cancel. And what do you get there, Victoria?
I'm putting it in right now.
Okay, go ahead.
I got 120.7323.
323, something like that. Okay.
Yeah.
So Victoria, this is the amount of time it's going to take for the 50 milligrams that we took in the beginning to reduce down to 2 milligrams. So Victoria, when we say 120, what do we mean? 120 what?
Would it be hours?
Hours, yes. It has to be hours because the half-life was given to us in hours. Okay, that's important. The half-life was in hours, so our answer should be in hours also. So that means it's going to take approximately 120 hours for that to be down to 2 milligrams. About 120 hours. Maybe you could say 121, that's fine. That's how many hours in a day? 24, right? So if I divide that by 24, it's 5 days. So it'd take 5 days for that to go from 50 milligrams down to 2. Yeah? Okay. Would you all like to run through another one? Just one more so that we really understand. Let's do a different substance. Let's not do something that you take like embedded medication. Although it would be kind of interesting to look at some illegal substances. That would be fun, but we won't do that. I don't want to get in trouble. Okay, so let's do something else. So how about like radioactive isotopes that are a result of like nuclear weapons? Okay, why don't we do something like that? So, I mean, I'm sure you all know that when a nuclear bomb goes off, when it explodes, anyone who's like in the vicinity is going to be like vaporized by the heat of the explosion, right? But that's really not what kills a majority of the people. What kills the majority of the people is the radioactive cloud that's created by the nuclear weapon. And so it basically, you have all this radioactive material that gets spread around by the wind, and it settles down onto people, and they ingest it. It goes into their lungs, gets into their body, and basically it's like a microwave. Okay, when you ingest it, it's like a microwave in the sense that the radioactive material gets into your cells in your body and it changes your DNA. Okay, so it kind of fries your DNA in your body, and then your body starts to become very sick because all of your cells don't know what to do anymore. So it's a microwave in the sense that it zaps your DNA into the point that your body stops functioning. I know this is really happy, cheery stuff I've got here I'm talking about, but that's the way radioactive material works. So let's take a look at radioactive material and let's look at the half-life of it. So I'm going to look up, let's go to Hiroshima. Hiroshima type of radioactive material. Let's see what kind of radioactive material was. I'm just going to go with this one. I'm not even going to read this, but yeah, it looks like uranium-235 was the radioactive material that was used for the bomb that was dropped on Hiroshima back at the end of World War II. I really hope everyone knows what I'm talking about here. So uranium-235, that's it. That's the radioactive material. So uranium-235 half-life. Anyone have an idea? Anyone have a guess how long it takes for the half-life of uranium-235? Any guesses?
I think it's in years.
Oh yeah, it's in years. It's in years for sure. Let's go for 700 million years. What? Is that not insane? Is that not insane? That means if you took a pound of uranium-235, 1 pound of it, that it would take 700 million years for it to go from 1 pound to half a pound. In other words, it doesn't go away. It's bad, it stays bad, and it stays bad for a lot longer than we've been around. So it's like a campfire that just doesn't stop burning ever. And that's why it's very difficult to get rid of this bad stuff. It's very hard to do. All right, well, 700 million years. Wow, that's a really, really big number. I'm wondering, should we stick with this? Should we? I guess let's stick with that. I mean, it's a real world problem. Okay. So uranium (235) has a half-life, oops, of 700 million years, not hours, right? Years. 700 million years. Let's find the decay model for, I'm just going to call it U235. That's the abbreviation for it, for U235. What am I really asking us to do here? When I say to define to find the decay model, what am I really asking us to find in that equation?
Okay.
K, right? So this is really saying, go find K. Go find K. Now, I know right now our number is going to be ridiculously small for K. So let's just run through the math on it, though. We're going to start with this. Okay. Here's our original master formula that we use. And now we're going to replace some things. I'm going to replace the left side with 0.5 because that's what we do every time we're trying to find a half-life. I'm going to replace this piece of 0 with 1 because that's always what I do when I'm given the half-life and I'm trying to find K. E to the K I don't know, but T I do know, right? T is 700 million. That's 7 with 9 zeros, or sorry, with 8 zeros. All right, so first thing we do, we take natural log on both sides. And that should be equal to natural log of E to the 700 million. Oops, that's 8 zeros, K. The natural log and the E go away. So I have 700 million K equals natural log 0.5. That's going to be, wasn't that the negative 0.693? Remind me, it should be. And now to solve for K, what do I have to do? Divide everything by 700 million. So I have to take negative 0.693, divide it by 700 million. And that should be our K. Now this is going to be a very, very small number. Negative 0.6, oops. Negative 0.693 divided by 7, 1, 2, 1, 2, 3, 1, 2, 3. Wow. Okay, so I think my calculator kind of gave up a little bit. So I'm going to do it on the internet instead. I'm going to do negative 0.693 divided by 7, 1, 2, 1, 2, 3, 1, 2, 3. Oh, it's not giving me a very pretty. So 0.99, okay. So yeah, you know what? I think I will go with what my calculator gave me. I would never give you a problem like this on the test, okay? I'm gonna give you Advil or some drug where you have a half-life that everything's nice. But I thought it would be interesting to look at something more real world. K should be approximately negative 0.000000. Hold on, I gotta count these. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 zeros in front of 1. 5, 6, 7, 8 zeros in front of a 1. That's what I got. So our growth model, we can now, or sorry, our decay model can now be looked at this way. We know what K is. Negative 0.1, 2, 3, 4, 5, 6, 7, 8, and then T. That's it right there. Okay, y'all doing all right? So now, with this model, if somebody wants to know how much uranium-235 would be present after a certain amount of time, we could use this model to figure it out, okay? Now, with that said, how many of you have heard of Chernobyl? You know what Chernobyl was? A city in Russia? I think I'm spelling this wrong. Yeah. Oh, I think. So Chernobyl, in case you are unaware of this, this happened. I'm not going to go through this. Wikipedia, we can't trust it anyway, but this should be good enough. So in, what was it, 1986, I believe? Yeah, 1986. 1986, there was a nuclear reactor. You can't really see this picture very well, but there was a nuclear reactor in Russia. And the nuclear reactor, they lost control of it. And there was a huge disaster. There was a huge explosion. And all this radioactive material was spread out throughout this city, Chernobyl, right? Let me see if we can find some pictures of. So it's actually really kind of crazy when you look at these pictures, because what happened is the explosion happened. A few people died that were there at the actual place, but all the people in the surrounding city had to leave because all this radioactive material was spread out everywhere. And to this day, nobody lives there. Still to this day, no one lives in the city. So if you go and you look at pictures, it's crazy. Here's a picture. This is like some building, and you can see, because they just all left. No one ever came back. The window is broken out over time. You can see like vegetation from the outside has started to grow onto the inside. And it's really kind of eerie if you go on the internet and you look at these images. Here's just like I don't know what this was. Maybe it was like a daycare center or something. They just left everything the way it was. There's a little toy doll in a little crib here. And so nobody goes back. It's like stay out, okay? And the reason why is because of the radioactive material that's still there has not gone away. So if my memory serves me correctly here, does anyone have a guess as to how much radioactive material they lost control of that day? Like how much of it was, anyone have an idea or have a guess? They had some uranium there. So does anyone just to think that whatever it cleared out a whole city even to this day, right? 1986, that's 34 years ago. People are still not there. Anyone want to just take a random guess as to how much bad radioactive material was in that reactor when they lost control of it? Take a guess. No?
600 pounds.
600 pounds. Okay, there's a guess. 600 pounds, that would be, that's a lot, right? 600 pounds. If my memory serves me correctly, it was 10 pounds, a little bit less than 10 pounds. I mean, that's like, that's like your backpack, less than your backpack, right? 10 pounds of this stuff, right? So what I'd like, now I don't know if it was uranium-235. I don't know that, but let's just go with this. And let's use this model. Let's answer this question. In 1986, 10 pounds of uranium. I think it was uranium-235, but I'm just going to go with it. In 1986, 10 pounds of uranium-235 was lost in Chernobyl, right? How much is there today? All right, so we have our master formula, right? Here's our master formula. Copy, paste. All right, so if I'm telling you that in 1986 there was 10 pounds, that would be how much we started with, right? And we want to know how much was there or how much is there today. So we want to know how much is there. And do we know how much time has gone by since this reactor, we lost control? Do we know the time? Well, 1986, right? So it's been 34 years. Is that right? So about 34 years. So all we have to do is replace that with 34. And if we do that, then we'll have an answer. So I will write P equals the amount that we started with, 10, e to the negative 0.0000000001 times 34. So I'm going to try and do this on my calculator. And I'm going to get, when I do this, and see if you can, okay? I get 10 times, now when I do all that on my calculator, I get, so that's times, I get 0.99999, 1, 2, 3, 4, 5, 6, 7 nines, 66. And then I'm going to multiply that times 10. And all that does is moves the decimal point over. So we get 9.9999966 pounds. So basically, what are we saying? 34 years later, how much is there? Practically all of it's still there, right? It's all still there. And it's not going anywhere anytime soon. That's kind of mind-boggling if you think about it, right?
So aren't people living in Hiroshima today, though, even after the atomic bomb?
Yeah, there are people. It has to do with how much of it there was. Like this was pure uranium-235, you know, and this uranium was not. It was spread out in an explosion, but it wasn't a nuclear explosion. Nuclear explosion would spread things out. Let me try and think about, if you have a huge explosion, everything's thrown out into very, very microscopically small pieces that spread in the wind. This, at Chernobyl, it was more like huge clumps. And so it stayed contained. It didn't get to go into the air. So when it gets into the air, it's bad, but it's a very low dosage that you get of it. It's a lower dose. Does that make sense?
Yes, it's less concentrated.
It's less concentrated, so it doesn't have as much of an impact. So in Hiroshima, they actually detonated the bomb above the ground. So the bomb actually came, it didn't hit the ground above. They detonated it above ground because it has a bigger impact if you do that. And so it was spread out into the atmosphere more, and it was able to dissipate. That's why back in the Cold War between the United States and the former Soviet Union, the big fear was not that we were going to kill each other by, you're going to be sitting at your house and you get a nuclear bomb dropped on you. That's not what we were worried about. What we're worried about is if there are 100 nuclear bombs that go off, then all this stuff is going to be mixed into the atmosphere. And it's not only going to kill people in the United States, it's going to kill people in Canada, it's going to kill people in Central and South America. It's going to get into the what do you call it? The Gulf Stream, not the Gulf Stream. What is it called? The stream of air that moves across the continent. Is it the Gulf Stream? I don't remember. But it's going to be all this radioactive material would be carried around the globe. And so you wind up, if you drop enough nuclear bombs on each other, you wind up killing everything, right? Because there's no safe place to hide, except the cockroaches. The cockroaches live. They always live, right?
Cockroaches and Twinkies.
What's that?
I have a question.
Cockroaches and Twinkies.
Yeah. Mm-hmm.
Did you get the 0.9966 right there?
So what I did on my calculator is I typed all of this in. right there to my calculator, and that gave me this 0.9999. And remember, I'm not going to give you a problem like this on the test. It'll be very much more, you know, like this one was, where the numbers are nicer and well easier to work with. The problem is that this constant we got, this growth constant or this decay constant, is just so small. Our calculator is kind of giving up on us because it's so small.
Okay. So I don't
All
think I
right.
got 34.
You got what?
I got 34.
Really? When you typed that in, did you raise e to that power?
I got the same thing as well.
You got 34?
Mm-hmm.
Yeah, I did E over the negative 0.001, then end parentheses, 34, end parentheses.
Okay, so
Gave me 33.9999.
when you put e into your calculator, right, you do e, and it asks for the power. Why don't you do this first? Why don't you, the best thing I think would be to multiply those two together first, okay? Get that number, and then take e and raise it to that number. I think the problem you're having is with the parentheses. What you're doing, the way you're typing it in, you're actually doing this part first because of the way your parentheses are. You're doing that first, and that's giving you a number that's really close to 1, and then you're multiplying it times 34 instead of the 34 being up here in the power in the exponent.
They say they got 33, right?
They're saying they got something close to 34.
33.9, etc.
Yeah, that's not right.
Oh, well, what I think they ended up doing is instead of putting the 34 up in the power, they
Yeah.
put it separately.
Exactly. So it's different for everyone's calculator, and that's why it's hard for me to show you like how it works for everyone. Carolyn, what kind of calculator?
Okay, I see. I got it now.
I have the TI 89 one, not like this one.
Okay, so let me show you how you would type that in. You would go E, and then it shows you a little caret, right, like this,
Yes.
and then do parenthesis, and then do negative 0.000, whatever that is, 1 times 34, and then close the parenthesis. Do it like that, and that way it's treating everything that's in here as if it's the power on E. I think what you're doing is this 1 and then times 34, and that's not going to work. This parenthesis has to be on the other side of 34.
Okay, so when I typed it all in like one parentheses,
Mhm.
it still just gave me 1. Right.
Oh yeah, it's rounding. Okay, it's rounding. So the number is actually 0.99999. So your calculator is okay. That's 1. Then you multiply that times 10. So again, it's basically telling you it's all still there, right?
Okay.
It's only been 34 years. It takes 700 million years for half of it to go away. So, all right. Yeah, I think that's it. Let's talk about the review. We only have 20 minutes left. So on this review, let's just go through and take a look at what I'm asking you to do. There's no way in 20 minutes I can do this whole thing. But the first part, yeah, let me just walk you through these, all right? Maybe I'll just kind of show you on each one how you would go about it. For the first problems, what I want you to do is sketch the following exponential functions. So all that means is for each one of these, you'll make a table. You're going to plug in x and then whatever the function is. So let's say we're doing this first one, 3 to the x. And then what you'll do is you're going to take, everyone's going to use the same numbers. We're going to plug in -3, -2, -1, 0, 1, 2, and 3. Everyone use those same numbers and plug those into that function. So that means you're going to do 3 raised to -3, then 3 to the -2, 3 to the -1. And you're going to do that for each one of these. Once you do that, each of these are going to represent a point that you're going to graph. So on a graph, just plot those points, and you should get something that looks like an exponential function. Does that make sense? We did this, if you want to go back, I'll bring that page back up, but we did this first class in November here. Here we go. So this is where we did it in class, exponential functions. And, you know, we made this table, and then we plugged in, we got these points, and then, you know, that's the day that we did. That was on the 10th of November. Okay, so that's what the first question is. And by the way, let me say something about this review. This review is much longer than the actual exam will be. I'm not going to ask you to sketch 4 different exponential functions on the day of the test. I'm probably just going to give you one of these, all right? But I wanted to give you a variety of questions to practice. All right, so you'll do that for each one of these. Any questions on that?
Yes.
Yes, there is.
Yes. 3 to the negative 3 is 1 over 27. Would you want us to convert that into a decimal, or just leave it as is?
I would do it as a decimal so that you can graph it. And now it's going to be hard to graph that number because this is 1 over 27. So that means if you go to negative 3, you're going to be very small number. So that's why what you'll do is when you put the number there, you know, you'll draw your exponential function. Remember, there's a horizontal asymptote. It gets closer and closer without touching. And as you move to the right, these numbers are going to get a little bigger and bigger and bigger and then real big, right, as you start going down this table. So for something like 1 over 27, just put a dot there. I understand that it's small. Does that address your question? Okay,
Yes,
good.
thank you.
Okay. All right, now after this, the next questions, these, let's see, numbers 2, 3, 4, and 5, all of these problems, 2 through 5, all involve either this formula or the shampoo formula. Okay, it's going to be one or the other. Can somebody remind me when it is that we use the shampoo?
When it's compounded continuously.
Yeah, anytime the question says compounded continuously, you're going to use shampoo, right? So this would be for that one and for that one. And that means that the other ones, quarterly, monthly, daily, those you're going to use this formula. So a lot of these two problems, at least these two, are going to be about, are you able to use your calculator correctly and plug things in right? Because on the day of the test, you know, it's all about getting these numbers correct. And that's why I've been telling you for the last week or so, make sure you're using your calculator that you're going to use on the test, because you can't use your phone on the test and you can't use the computer on the test. So get used to the calculator. So let's see. So like, let me just set this one up.
Sir, I have a question.
Yeah.
So are we just gonna have to memorize all these formulas, or will
Oh no,
we be able to, like...
I'll provide these for you.
Oh, okay, thank you.
I'll provide these, and I'll provide the exponential growth decay model, the one that we were just using for the Zoloft and stuff. I'll give you that also. Okay, so like for this one, you know, $15,000 is placed into a simple interest account. I give you the interest rate. Say how much money would be in the account after 4 years. So I give you the amount that we put in, the interest rate R, and I give you the time T in years, right? So you're just going to replace R and T and P with those numbers. And then for this green formula, the N here depends on this right here. So if it's quarterly, what would N be?
4.
4. And if it's monthly, it would be, the N would be 12, right? And here for this one, if it's daily, it would be 365 that you'd put in there. I never did an example with daily. I never gave you one. So this is the first time you're seeing it. See how it works out. The only difference between number 2 and 3 is that number 2, you're putting money into an account and you're going to get money back. Number 3 is you spent money on a credit card that has a huge interest rate, and it's saying how much would you owe if you don't make any payments for 3 years. So here you're making money, here you're going to lose money, right? Now, number 4 says you want to put $500 into a 5-year CD, and it asks for the interest rate that you'll need in order to have, well, there's 2 questions here, $750 at the end or $1,000 at the end. And it says it's compounded continuously. So that means we want to use this formula. I'm telling you, you're putting $500 in, so you know that P is 500. I'm telling you it's going for 5 years, so you know that T is what, 5? And I want to know what the interest rate needs to be. So what we're trying to figure out is this, right? What is the interest rate? What would the R be if you know here that P was 500, T was 5, and then what's A? What's A going to be?
Would it be the same?
The 750.
Yeah, so for part A, that you just replace A with 750. For part B, you'd replace A with 1,000. So these are two separate questions saying, hey, what do you need? What interest rate do you need to get 750? Then the other one's like, oh, well, what interest rate would you need to get $1,000 after 5 years? So to solve number 4, you're actually going to need to be able to solve a lot. You're going to need to be able to solve an exponential equation, which means you're going to need the natural log, right? You're going to need that because you're going to have to get that R out of the exponent, which means you'll have to come in with an E on both sides at some point. So there's a big difference between problems, problems 2 and 3. Those you're just plugging into the formula and you're using your calculator, no problem. Number 4, you're trying to solve for a variable that's up in the exponent, so you have to use the logarithm. And then this one is the same thing, but it's a little bit trickier because all it says is you put some money in the stock market, which has a return of 9.2%. So it's, again, it's that's your rate. How long would it take? How long would you need to leave your money in there if you wanted to double your money or triple your money? I'm not going to tell you right now how to do this problem. I've talked about it. I talked about it in class. Okay, we did a problem where we actually did doubling our money, but I want to see how you do with this. All right. I will tell you it is this formula though. I mean, it's still this formula. You just have to think about what it means if you put some money in there, what it really means when we say double your money. What does that mean? That side has to be. I want you to think about that, right? Okay, let's move on. How are we doing? 720, 1020. Okay, so the next few problems are all very mechanical problems. This is very much like what we did last class. Number 6, these are all exponential equations. You're trying to solve for x in all of these. And so what they do is they get progressively harder. Like the first one, you're trying to solve for x, so you just take natural log on both sides. And you do that because the e to the x is isolated already. And then as you move through these, they get a little harder and harder. You have to move the 7 over, and here you have to move the 7 over, divide by 3 before you can do the log. We did this last class, all right? So I'm gonna let you, and this was also kind of like a homework assignment that you have. So you got those to practice, and then these are log equations where you're trying to solve for x, so you have to kill off the natural log, so you come in with e on both sides. Again, we did that last class. And then here, this was last class also, we're trying to kill off the 5 to the x, but we can't use the natural log, we have to use the log base 5 to kill it. And then you have to use that change of base formula that I gave you last class. Okay, that formula is going to be necessary for this. And then here, yeah, we talked about this last class. So I think these, you know, like if I were you, I might actually just start with these. I don't know, you do what you want, but if you can do these, it'll make the other problems before this a little easier. And then the last question is the ibuprofen problem. So I give you the growth decay model or equation, and then I give you the half-life of ibuprofen is 3.5 hours. I ask you to find the decay model, so find K. And then once you find K, it says you take 400 milligrams of ibuprofen. How long will it take it to decay down to 1 milligram left in your body? So you see that's very much like the Zoloft one we did, right? All right, questions?
Will you send us like the answers before the test, like a day or two before?
Yeah, I mean, I'm going to try and get these answers done before. I was hoping I could work through the whole thing today, but I don't want to rush. So yeah, I will send you the answers. Why don't you give me till like Saturday? Should be able to get them by Saturday.
Okay.
Okay. And I'll send that out through Canvas email, but don't wait for the answers to start trying to do the problems. I would say use the answers as like to go back and check and see what you did right or wrong. That's probably a better thing for you as far as reviewing. Okay, so at this point, it's 10:30. I'm going to now just leave this session as an open session. If you'd like to start working on the review, I'll be here. I'll answer any questions. And if you feel like you want to go and work this on your own, you want to leave the session, you can. All right. Okay, so I'm going to stop recording, but I'll leave my screen up and I'm just going to turn my camera off, but I will be here.